But what about the other part of the inner ear, the otoliths? Well, I'm going to tell you things which are very new and to many of you will be very strange, because there's been a huge amount of work on otolith function, and it's shown that most of the old ideas about the otoliths here just being sensitive to tilt, that's true, but they are just so incomplete. These sensors in the inner ear are doing much more than being sensitive just to tilt. They respond to sound. They respond to vibration. I've shown that in the guinea pig, and I will show you how here. These are the way people used to schematise the otoliths. Here, the utricle and the saccule is drawing flat plates of receptor cells, polarised, and with these beautiful images showing the otoconia like this. By the way, these otoconia don't really sit like that. Otoconia have got things like reinforcing rods going through the crystals. They're held in place very firmly in most people by essentially biochemical reinforcing rods, not by just floating around. Very interesting why they're displaced, but I'm not going to go there now. And of course, people have simplified things like this. They say that it's head tilt is what activates the otoliths, and of course that's true. But what's new? Well, what's new is when you look carefully, those receptors are not uniform at all. There are big variations across those receptor surfaces. They're very sensitive, like canal receptors. In fact, the sensors in the vestibular part of the inner ear, the individual receptor elements, are almost as sensitive as cochlear receptors. When people have actually got in and deflected them by these nanometer amounts and measured the response, and they just are remarkably sensitive. It's not the sluggish system that people have thought of for so many years. Nanometers are the threshold down there, and they're activated by sound and vibration. And that's turned out to be very useful for testing, for identifying what's going wrong with these otolithic structures. So let me show you this kind of variation. This is a view looking straight down on one of these receptor surfaces. This is from Japanese researchers in 1967. This guy actually drew by hand every single one of those receptors. Every dot on that is one receptor. Just extraordinary, and of course it's been confirmed by results since. But everyone in the room can see this dark band here. It's a specialised region where there are very fast receptor cells that look like this, called type 1 receptors, with a hair-like projections projecting up into that otoconial mass. And if you look straight down on it, you can see here, that band here called the striola, and you can see that the receptors there are in fact shorter. And this shows you exactly so. So the idea that you've got these simple receptors that are all the same height all the way across this uniform membrane is just totally crazy. Here, some receptors at that striola are 5 microns high. Other receptors are 30 microns high. It's a highly differentiated system all the way down in the periphery. And that shows you even more clearly. This is a chinchilla. You don't need to worry that it's a different species. The human is very similar to this. We know that. And that's that region that I described. Oops, there. And these other type 2 cells have got very different characteristic responses. But here are the short guys and here are the tall guys. These huge cilia projecting up into the otoconial membrane. Well, I studied these by recording from single nerve cells in guinea pigs, anaesthetised guinea pigs, and presenting sounds and vibration and finding out whether these vestibular receptors, nerve cells actually respond to sound and vibration. And many of them don't. Most of them don't. They just don't do anything to sound and vibration, which is very disheartening. But in fact, some of them respond incredibly strongly, like this guy. This is responses from one single neuron here. Each spike is one action potential going down that cell. And this is vibration, and you can see the increase in firing to vibration and the increase in firing to sound. This is not a cochlear neuron, this is a vestibular neuron. And I know that because I traced it all the way back, inject a tracer, and it comes from the utricular macula of the guinea pig, which looks like that. So now we've got a system, the vestibular system, which is giving the brain, actually part of it is giving the brain information about sound and vibration. And these are thresholds for a whole host of different neurons to different frequencies. These are vibration frequencies, 500 cycles per second, 1,000 cycles per second. And when you come right in and look at it carefully, in fact, when those neurons fire, here, exactly when they fire, is locked to the stimulus, just the same way as it is in the cochlea. That phase locking occurs for vestibular afferents as well as for cochlear afferents. The brain is getting complex information from these structures which people have simplified for so many years as just responding to tilt. This is their response, their threshold to sound, okay? And the two regions respond, have got very different thresholds. For me, it's extremely exciting to see what might be happening. And just very recently, we have used the fact that this macula, this structure sensitive to gravity, in fact is not attached to bone, it floats. It floats. And it's suspended like a hammock. There are fine fibres that take this sensory system and suspend it like a hammock. And I think this is the key to understanding how this system actually responds to sound and vibration. With Daniel and Chris, we've used laser techniques very recently to show that during sound and vibration, this whole vestibular sense organ moves up and down, locked to the stimulus. And different regions of it move differentially. This is fluid dynamic modelling, finite element analysis modelling from a colleague in the US showing different areas of this macula responding differently to different frequencies. This is an entirely new understanding of how the otoliths work.